Welcome back to NE 630 Nuclear Reactor Analysis course. So last time we started solutions for the diffusion equation, and we started by solving the diffusion equation in non-multiplying media where you do not have any fissile material present in the medium. And we stated that we will solve first for infinite medium where you have a localized source at the center, and then we will try to solve for finite systems and see what's the difference between the infinite and the finite system. Then we will be moving to the case where we will put a fissile material inside the system and try to solve again for infinite multiplying system and for finite multiplying system, and we will add a reflector around the finite system and see what's the effect of reflector and so on. And all those solutions, by the way, are carried using the one group diffusion equation. So you consider that all the energies, you condense it to only one group. So you average everything over one group, and you consider the neutrons are moving with the same velocity. So today we'll continue also the same business. Last time we discussed the infinite plane source. Today we'll go through the linear or line source and the point source. So let's continue the fun. So if we consider an infinite system, and this is the line that goes to infinity in both directions, so infinity and negative infinity, so like this. One more thing I want you to focus is when you look at the source, the plane will usually emit neutron per centimeter square because it's an area. What do you think for a line? Yeah, but it will be per unit length. So you will emit, the source will be number of neutrons per unit length per second. And for a point source, it will be number of neutrons per second, because the point does not have any dimension, so that you will divide by the area or by length or anything like this. So again, diffusion equation, 1 over the velocity, dphi by dt equal to source plus nu sigma fission minus sigma absorption phi minus or plus d Laplace square phi. Again, with non-multiplying, we have this term equal to 0. Stationary state or steady state, we have this term equal to 0, and we will end up with this type of equation. And last time we said that we will have just the equation be written as Laplace square phi minus 1 over L square phi equal to 0, where L is just equal to d or sigma absorption over the sigma absorption, or d over sigma absorption, and this is the diffusion length. So now, if we try to solve, we stated last time that the appropriate coordinate system will be cylindrical coordinate system. So you will imagine that you have a cylinder like this. This is the center of the cylinder here, and this is x, y, and this is the z direction. But in cylindrical coordinates, usually you will have this is the z, a point here on the cylinder. It has a height z, radius r, and angle phi. By the way, let's call the angle theta so that you will not be confused with the flux. So now you have two things. The cylinder, the line source, will go from negative infinity to infinity in the z direction. So you do not expect that you will have any dependence on the z direction for the flux. Yes? Because the line goes from negative z to infinity to plus infinity, there is no dependence. Also, if you move around in the theta azimuthal direction, you do not expect that you will have any dependence, any change in the flux around the linear source. So you will eliminate theta, and you will eliminate z, and only you will expand in r. So what's the component in r for d2 phi by dr square? It's 1 over r d by dr r d phi by dr minus 1 over L square phi equal to 0. Of course, this is the r component for the nabla square. And there is z component, which we eliminated because of the symmetry, because of the infinite source in z. And we eliminated the theta because of the symmetry. So we eliminate z because of infinite, and we eliminate theta because of the symmetry. I have to warn you that a couple of your friends, last year, when I asked them to solve this, they make a very, very extremely bad mistake. They cancel this r with this r. So do not ever do this. You cannot cancel this r with this r. Do not ever. 60% of the students fall into this mistake. Do not ever. There is a differentiation d by dr in front, so you cannot do this. Again, also they did, when I asked them to get the average, they wrote the average as f of e dE divided by f of e dE. They cancel f of e up and down. Do not do it. There is at least half of the class did this last year. So, and students were complaining from me because of my mathematics, not from them. So please do not do this. I'm just giving you examples of trivial mistakes, and the students, he think that he is right and I am wrong. So now, how we will solve this one? So if you will do the arrangement for this, you will notice that, let's do it here. Multiply by, let's say, r. So when you multiply by r, you will end up with this is r, and then this will be first multiplied by the differentiation of seconds plus second multiplied by the differentiation of first, which is 1, minus r over L square phi equals 0. Then if you multiply all terms by r, this will give you r square r square, and this will be the form. So this is in the form of d2y x square d2y by dx square plus x dy by dx plus n minus multiplied by y equal to 0. I think this is x square minus n square, something like this. Multiply it. So this is, I think, x square minus n square multiplied by y. What's this? Yeah, this is Bessel function. Thank you. Bessel function. And this is Bessel function of order n. If you have this is negative, so it will be the modified Bessel function. So if you have, instead of positive, negative, it will be the modified Bessel function. And if n equals 0, this will be the first order for the or the 0th order of the Bessel function. Usually the solution for this one will be y equal to some constant multiplied by I naught of x plus b y naught k naught of x, usually the solution. And I naught, modified Bessel function, this is the Bessel function, and this is the, both of them, Bessel functions of the 0th order here, and we will show in a minute what we mean here. So if you try to solve this one, now the solution will be phi of r, because you are solving in r direction, equal to some constant a multiplied by I naught of r over L, because the x here is not x, it's r squared over L squared. So you will take r squared over L squared. You will take this plus b multiplied by k naught over r over L. Okay. So I naught and k naught are called modified Bessel functions. Again, because you have a negative sign here, it is the modified. If you have a positive sign, you will end up with j and y. The Bessel functions will be j and y. If you have negative, like what we have here, it will be the modified I and k. So they are modified Bessel functions of the first, of the 0 order, of order 0, and again 0 because the constant here n is 0, order 0, and they are of the first and second kind. Of first, this is the first kind, this is second kind. First and second kind. So first kind, second kind. Now, what do you expect? Again, we need how many boundary conditions to satisfy? 2. First thing is, again, flux at infinity is constant, is 0. We will notice that at r goes to infinity, this I naught does not go to infinity at r equal to infinity. It does not go to 0. It goes to infinity. It became infinite. So I have to suppress this one. So this will give me what? A equal to 0. What's the second condition that I have to apply so that I will solve this one? Again, when we solve the equation, we solve what equation? The homogeneous equation. Where is the source? The source at r equal to 0, it's a delta function, delta of r. Yes? But I can solve the y particular integral, which is this one. Then I have to solve for the complement, this is the complementary function. Then I have to solve for the particular integral. But last time I stated to you guys that I will not solve the particular integral, but I will solve the source condition. And what's the source condition? Source condition is when you shrink, there is neutrons coming across this surface in all direction, 4 pi, but they are going in the r direction. So when you shrink this until it just touches and it became the surface area of this line, this is the source term. Yes? So the condition will be what? The condition will be limit when r tends to 0, when r goes to 0, current. Yes? But the current is how? What's the current? Number per centimeter square per second. But the source is number per what? Per centimeter per second. So I have to multiply this by what? By some length. Yeah, so I have to multiply it to 2 by r. What's 2 by r? Circumference. And because I have a unit length in the z direction, so this is the area. So this will be what? Total number of neutrons per unit length of the source. And this is equal to what? S naught when R go to 0. So when you will do this, how you will do this? How to get the current? So the current J is nothing more than negative grad phi multiplied by D. And what's grad phi? What's gradient in the cylindrical coordinate? What? Yes, so it will be negative d phi by dr. So when you do this, you will differentiate this, multiply it by what? By phi. And we already eliminated A, so you will only take this differentiation for this term only. And then you will get B from there. So we eliminated this because of what? Infinite boundary condition. We'll end up with this. We'll use this equation to get the current. And then once we get the current, we'll have only one constant. From here, the constant will be related to what? S naught and what? And D. When you substitute now in the equation with B, you will notice that phi of R is just equal to S naught multiplied by Q naught of R over L divided by what? 2 by D. And that's it. So this is the flux. Okay, guys? Easy enough? So now what we did is we solve the equation. We solve the equation for an infinite source, line source. Let's go ahead and solve it for a finite medium. So our medium is no longer infinite. Our medium is like this. The line source is infinite, still infinite the line source, but our system goes up to R capital. Or in the book, he call it A, diameter, radius A. Now, what's the boundary condition now? Flux will be still the same, phi of R equal to A multiplied by I naught of R over L plus B K naught of R over L. Still exactly the same. What changes now? Boundary condition. Go ahead. Yeah, cylinder is infinite in the same direction of the source, but it has finite radius. And instead of R over A, at A, it will be flux at A extrapolated is equal to 0. And A extrapolated is just A plus 0.7 D. And D is the extrapolated distance. So it's this distance is 0.7 D. So if you add 0.7 D to A, this is now A tilde, the extrapolated distance. Okay, guys? And what's the other condition? Huh? The source 10. Do you think there is any change for the source 10? Nothing. So it will be still the same. So now, if you do this, you will notice that the flux as a function of r will be a little bit complicated. It will be, of course, I will not cancel a. Why? Because I have a finite what? Dimension. So I cannot say that this term is equal to 0. Yes, guys? In infinite system, I have this term equal to 0 because flux is finite at infinity. But here, I do not have infinite system. Yes, go ahead. Okay. So in this case, I will have both I naught and K naught. So you will notice that I will have I naught A extrapolated or A tilde. So call it A tilde, call it A extrapolated. So to be consistent, I will call it A tilde divided by L multiplied by K naught of R over L minus K naught of A tilde over L multiplied by I naught of R over L, all divided by 2 pi d I naught of A tilde over L. So I naught A tilde over L, this is a constant. Why? L is what? Yes?
Last time you had D equaled 0.7 lambda extrapolated.
Yeah.
So A tilde was A plus D, not A plus 0.7 D.
Okay, call it lambda 0.7, sorry, lambda extrapolated. Thank you. So you call it A plus D or A plus 0.7 lambda extra, whatever. So this is constant. I naught, the Bessel function of the first kind, the coefficient or the parameter inside the I naught is A tilde, and A tilde is constant and L is constant. And this comes from the first constant A here. And the second constant is what? It's K naught of A tilde over L. But this is the variable. K naught of R over L and I naught of R over L. And this is also a constant. This is constant. So this is constant, this is constant, this is constant. Those are the two variable functions here. Let's move and try to solve it now so we got the cases that we solve infinite system with plane source, infinite slab with plane source. Now we solve infinite system with line source, finite cylinder with line source. Now let's solve point source in infinite homogeneous medium. So let's solve the point source. Point source in infinite medium. So you have a point in the middle of nowhere, like here in Manhattan. Okay? So this is a point in the middle of nowhere. So you have infinity everywhere, a point. Then if you look at this point, you will make your imaginary surface to be what? A sphere symmetric around this point. The point will be the center of the sphere. So this will be what? R. Now, equation that will be solved is nabla square minus 1 over L squared phi equal to 0. What's the expansion here? Last time we said 1 over R, d by dr, r d phi by dr. Again, here I will have 3 dimension in spherical coordinate, r, theta, and phi. But you will have azimuthal symmetry, and you will have what? You will have polar symmetry. So in these cases, I will eliminate theta and phi, and I will only keep the r direction. So I eliminated two coordinates because of the symmetry. Last time I eliminated 2 coordinates also, one because of the symmetry and the other one because infinity. It's infinite direction in z, so there is no change. But here I am eliminating both because of what? because of symmetry, not because of infinite dimension. So here is r. Then this will be 1 over, instead of r, it will be 1 over r square d by dr, r square d phi by dr, and negative 1 over L square phi of r equal to 0. There is a trick to solve this problem. So if you just see a problem like this, just spherical coordinates, and you want to solve nabla square. If nabla square phi equal to 0, this is called Laplacian problem. Okay, if nabla square phi equal to some function, it would be Poisson equation. You solve Poisson equation. Okay, so you are solving second order differential equation, and you have nabla square in r direction. So the best thing to solve it is to do change of coordinates or change of variables. To do this, so we will say that the flux, I will say that the flux can be represented as psi equal to phi over r. Okay, guys? So I will do it like this. So to do this change here, so phi will be equal to r psi. If you do this change, you will notice that d psi by dr is nothing more than 1 over r square, and this will be what? This multiplied by d phi by dr minus multiplied by dr by dr, which is 1. So this will give you what? R d phi by dr minus phi divided by r square. Yes? So if you try to reduce this first, this will be 1 over r square, and r square multiplied by d2 phi by r squared, and then plus d phi by dr multiplied by 2r. Yes? Minus 1 over L square phi of r equal to 0. If you multiply by r square, or if you multiply by r, let me try to simplify it. So psi equal to phi over r, or phi equal to r multiplied by psi. D phi by dr is nothing more than first multiplied by the differentiation of second plus second multiplied by the differentiation of first, which is 1. Then differentiate it again. d2 phi by dr square is equal to first multiplied by the differentiation of second plus the second multiplied by the differentiation of the first, which is 1, plus the differentiation of this one, d psi by dr. So this will give you r d2 psi by dr square plus 2 d psi by dr. Okay, so let's see. So r square will cancel with r square, and you will have 2 over r square, 2r over r square, so this will give you 2 over r. 2 over r. Then this will be, if we multiply by r, so this will give you r d2 phi by the r square plus d phi by the r, because we eliminated the r, minus 1 over L square r phi equal to 0. R phi is equal to what? R phi, is it R phi? Phi over r. I have to get r, phi over r. Let me think about it. So we'll put this one here. We'll substitute with this one. This will give you r multiplied by r d2 psi by the r square plus 2 d psi by the r plus d phi by the r is nothing more than r d psi by the r plus psi minus 1 over L square multiplied by r, and phi is nothing more than r psi, so this will be r square psi equal to 0. Then to simplify it, I think I made a mistake, but I have to return back to this one. I will hold on and I will think a little bit about this one. I made a mistake in the substitution, but anyway, you will have turn this equation to something like in phi, in psi, d2 psi by the r square plus something like psi over L equal to 0. Something like this. You will reach to something like this. There is a mistake here, I made it here. So what's the solution for this equation? Psi equal to a e to the power of what? R over L plus b e to the power of what? Minus r over L. Because this function is what? M square plus 1 over L square. I think it will be minus here. Equal to 0, so M will be plus or minus 1 over L. But what's psi? Phi over R. So your flux at the end will be a e to the power of minus r over L, or plus a over L divided by r, and b e to the minus r over L divided by r. I have to return back to this one. If I have time, I will return it back and I will give it to you. But this is usually how to solve it.
Maybe phi equal r psi.
What do you say?
Phi equal r. Sorry, psi equal r phi. This must be the assumption.
Yeah, maybe. So I have to return it back and look at it. But this is the correct answer for the problem. You will transform it using the new function psi. Then you will return it back and divide by. You will say that okay, psi is just phi over r, or phi is psi over r, and you will divide by the r, and this will be the solution. So let's look here. It's a point source and it emits neutron per number of neutron per second. There is nothing. So the first thing is So what will be the first boundary condition here?
Infinity equals 0.
This is infinite system. Yes? Which one will be eliminated? Although you have an r here, and at r equal to infinity, this will give you 0, but you still have infinite term upstairs. So this would be gone, and you will end up with this. Yes? Yes, guys? So you will end up with this. So this is the first thing. R goes to infinity, A should be equal to 0. The second one is the source term. What's the source term? What do you expect? Limit for the current when R goes to 0. The current is number per centimeter square per second. But the source emit number per second. So I have to multiply by the area. And surface area for the sphere is what? So this would be 4 by r square, and this will give me S naught. So when you do this, you will end up with the flux equal to S naught e to the power of minus r over L divided by 4 by r d. So this is the flux for a point source in an infinite medium. Flux for a point source in an infinite medium. If you solve the same equation, but for a finite sphere, so here is this one, psi equal to r phi, not phi over r, and I can give you okay, so let me give you the correct ones here. So d psi by dr is equal to r d phi by dr plus phi. d2 psi by dr square is equal to r d2 phi by dr plus d phi by dr multiplied by 2. Then if you will substitute, instead of this would be phi r and psi over r for the flux. And then if you substitute this into the equation, the equation is just 1 over r square d by dr, r square d phi by dr, minus 1 over L square phi equal to 0. Expand this, so this would be 1 over r square d 2 phi by dr square multiplied by r square plus 2r d phi by dr minus 1 over L square multiplied by phi equal to 0. Then r square will cancel with r square here, and r square will be 2 over r here. And then if you will use those two equations, so you will have d2 phi by dr square plus 2r over r d phi by dr minus 1 over L square d phi by dr. So this you can write it as r d2 phi by dr square plus 2 d phi by dr minus 1 over L square r phi equal to 0. So r phi is equal to psi, so this is just psi. And the two term, this one You will get it from here. So you will transform the equation to d2 psi by the r square minus 1 over L square psi equal to 0. And this is the equation I told you that you have to solve. So the equation is d2 psi by dr square minus psi over L square equal to 0. So again, so psi will be like this, and phi is psi over r. It will be like this. So maybe I will conclude. I have still 5 minutes with slab geometry with a finite planar source. This is what we solved last time, but we just give the final expression without solving. So maybe it will be a good training exercise for you if I solve it. And then next time we'll start defining the kernel and diffusion kernel and so on. So again, guys, when you solve those problems, just put in mind that what's the coordinate system that I will be utilizing to solve the problem according to the symmetry of the source. If I have a finite, infinite source in infinite medium or infinite source in a finite medium. First thing you say, okay, here is a source. Is it finite or infinite? Okay, it is in a medium. The medium is infinite or finite. This will tell you, okay, what geometry that you will be using, what equation that you will be using. You will be using exactly the same equation. Nabla square phi minus 1 over L square phi equal to 0. This equation is what? Steady state. What else? Steady state? Yeah, I'm not talking about the assumption that we use in deriving the equation. But this equation, steady state, and it is homogeneous. The properties like the diffusion coefficient is homogeneous. So it's a steady state and homogeneous. So it depends now how you will tackle this problem on, am I going to solve it in Cartesian or spherical or cylindrical, and what's the source condition that I will be using. Should I take the limit over J only, or J multiplied by 2 by R, or J multiplied by 4 by R square? And all this stuff will come from the symmetry of the problem itself. So let's look for a slab geometry with infinite planar source, the one that we studied last time. Here is the planar source, and this is from 0 to A, but we have an extrapolated distance here and an extrapolated distance here. And this is A again. And you have sigma absorption, and you have a diffusion coefficient, and so on, and you have the source number per centimeter square, because this is plane you'll be now simplifying this to d2 phi by the x squared minus 1 over L squared phi equal to 0. And the flux as a function of x is nothing more than a e to the power of minus x over L plus b e to the power of plus x over L, or vice versa. So the flux now, the boundary condition is the flux at the extrapolated distance, plus or minus a tilde goes to 0. Now, I told you last time, if you have a finite system, you can use sine and cosine. Yes? I am doing this one here in purpose, using exponentials to show you how to transform it to sine and cosine. Okay, guys? So this is A and B. So this is A tilde. Now, all what you will do now is you will substitute here with plus A tilde. So this will be phi at A plus D. A tilde is A plus D. Substitute A e to the power of minus x will be A plus D. A plus D over L plus B e to the power of x is A plus D divided by L. There is a negative, there is a positive here. So this is the flux for A and B. Okay. So what's B now? And this is equal to 0. So I can get B as a function of A. So B is equal to negative A e to the power of minus 2 multiplied by A plus D divided by L. I got one boundary condition. I will take just the positive half of the problem. Now I will substitute the flux as a function of x. I will substitute here, would be equal to A and then e to the power of minus x over L plus B, but B now is equal to negative A. I took A outside, and this would be e to the minus 2 A plus D over L. So this is the first one. I have one more constant that need to be determined, and it's left, so I have to use source condition.
You can multiply that by e to the negative x over L, though, because it's...
Yeah. Actually, it is positive, not negative. Thank you. Now you will use the current equal to negative d free by dx, and then use limit j when x goes to 0 equal to the source over 2. When you do this, you have to do what? You have to take the derivative of phi, d phi by dx, and then multiply it by d to get the current. Substitute here, then you will get the constant A. So this will give you the constant A is just SL over 2D multiplied by 1 plus e to the power of minus 2 A plus D over L. Then you have to substitute back on the flux. So the flux is A multiplied by this, and A is SL over 2D multiplied by 1 plus e to the power of minus 2 A plus D over L. All of this is multiplied by 1 e to the power of minus x over L minus e to the power of x over L minus 2 A plus D over L. I think think there is. Then when you do this, just it will be S over L over 2D, and this will be e to the power of minus x over L minus e to the power of x over L minus 2 e plus d over L, and this would be, I think, 1 plus e to the power of minus 2 a plus d over L. And if you take just the positive half and try to do the substitution, this will give you S over 2d L e to the power of minus absolute value, as we stated last time, e to the power of x over L minus 2 a plus d over L. All of this is divided by 1 plus e to the power of minus 2 a plus d over L. To simplify it, this will be S over L 2d, and then you will multiply by e to the power of a plus d minus absolute value over L minus e to the power of a plus d minus the absolute value of x, or over L divided by e to the power of a plus d over L plus e to the power of minus a plus d over L. This is e to the power of something minus e to the power of something over 2. This is the shine, and this is e to the power of something plus e to the power of minus something over 2. This is cosine. 2 will go from upstairs with 2 from downstairs, and you will end up with shine a plus d minus x all over L divided by cosine a plus d over L, and all of this is multiplied by SL over 2D. So stop here, continue next time. If you have any problem, let me know.